Good morning, afternoon, evening, wherever you are. Welcome to this ARM Dev Summit session about demystifying virtual graphics. My name's Daniel Stone. I'm the graphics lead at Collabora. We're a global open source consultancy. And yeah, today I just want to try to give a bit of a picture of not only some of the use cases that we have for virtualized graphics, but also how it works under the hood, the trade-offs of some of the different approaches that we have and that we see, and also where the industry is going, and try to give you a picture of not only where things are now, but where they're going to lie as well. So yeah, we'll walk through kind of the demand, the use cases to begin with, and then go on down into some of the details, and hopefully leave you with a better idea of what can be a relatively confusing space. So in terms of where we see virtualized graphics, it turns out the answer is everywhere. You know, when I first started working with graphics, it was a very immediate, graphics is what's put in front of your face. It's the CAD app on your workstation, it's the games that you're playing, and it was a very immediate user-facing kind of thing. But here we are in 2021, we have machine learning taking over everything. We have a lot of offline workloads and GPU compute, both way up in the sort of HPC space, but surprisingly pervasively, just running through everything from from ADAS to image processing. It's everywhere under the hood now. So just as we've had to virtualize CPUs, GPUs are sort of going in that same direction. So if you look at the lower end in terms of capacity, on your client and your single purpose, what some people term embedded devices, we've got a much more complex model where we have single silicon, but we have multiple assurance domains and multiple boundaries within that. So the obvious one would be automotive, where you have your shiny media app, your shiny navigation app, and that's all nice and whizzy, but also your speedometer, your instrument cluster, not only are they using the GPU to present the content now, but they're also sourcing content from the IVI side. So that's a very obvious place where we have two domains within single silicon with very different properties that obviously can't share a single host system. If you look at desktops, things like Chromebooks as well, that's another area where the industry has been moving to a very trusted and assured base for the client system, but then running arbitrary applications inside sandboxes, and often these days now virtualized. The data center is a pretty obvious one. They started this whole trend of sort of commoditizing CPU time, and now they're offering GPUs as well, but at a huge price premium because they're a relatively limited resource, and they're sort of one of the high margin offerings. But as much as it breaks my heart as a graphics person to say that we're not special anymore, GPUs are becoming commoditized, and there is this demand from data center users, not just on the HPC side, but in more general purpose workloads, to be able to use and access the GPU as part of their work. And in the middle of these two, you have edge workloads, which is kind of, bridging that gap. And these tend to be virtualized just because of that in-between nature. You have heavily virtualized and containerized workloads in the cloud, and then you have probably virtualized workloads on the client system as well. So this tends to be an odd kind of in between, where you really feel the pressure of workloads being heterogeneous. And then also, one really important use case that has really taken off in the last sort of 2 to 3 years in particular, is this kind of hybrid and streaming model. So it's almost back, I suppose, to the network is the computer from for any of you who are old enough to recognize that slogan. I have a wonderfully powerful workstation and a lovely new phone, but a lot of people don't. And what they do have is very low latency, very high capacity networks. So cloud streaming of games and even some apps in the kind of subscription model is another demand push that we're seeing on that side. So if we look at how we virtualize graphics, there's 3 approaches, and none of them is better or worse than the other. They've all got their own trade-offs. So that's the direct, mediated, and API streamed solutions. This is all very sort of broadly speaking. It's not necessarily to scale, but it gives you an idea of where the trade-offs lie of each of them. So if we look at direct virtualization, this is something that most vendors will offer you. There will be a way for a guest to directly access some subsection of the hardware, be it a separate IP block or a partition within the same IP block with its own isolated context. In this sense, it's very similar to how we virtualize CPU time at the moment, other than there's no hardware standard for this. Between each vendor, between different generations of GPUs from the same vendor, even between SKUs, we do see this huge variance in how it's addressed, how it's used. And so unlike the CPU side world, where we have very well understood and very standard interfaces and primitives for doing this virtualization, on the CPU it's completely up to how the vendor does it. So I'm not really going to go into any detail because the vendors will thank me not to. These are proprietary details of their GPUs that they don't like to talk about. And it does often tend to be a more premium feature, either with SKU binning or licensing fees or something like that. So if you want to find out more, ask the vendor of your choice. The good thing about this direct virtualization is, although we can't really reason about the security because it depends on the particular implementation, it is the highest performance. There's really no substitute for going direct to the hardware and having that ultra high performance direct channel. At the other end of the spectrum, we have API virtualization. And this is kind of meeting the virtualization barrier at the level of the standards where they are. The standard in graphics is OpenGL, it's Vulkan, these kinds of APIs. And the API virtualization essentially just captures these API calls, translates them across the virtualization barrier, and then inside the host it will replay them as if the guest were running natively on the host. So that's extremely portable because everyone ships these APIs, everyone conforms to them, but it has the lowest performance ceiling because we're incurring more overhead and we're not necessarily capturing, we're not necessarily drawing that line at the place where we can get the highest performance. And it does incur processing load on the host to track and execute these things. Somewhere in the middle, we've got this mediated approach. There are 1 or 2 major vendors who offer this as a sort of native product. This is a bit of a halfway house where you get almost direct hardware access, but it still requires some explicit mediation between the host and the guest. So both of them have to be aware of the specific hardware, they have to be aware of how they're being virtualized, and there is a little bit of a performance requirement on the host to mediate and to forward calls between the guest and the hardware. So it's not fully direct. It does have a bit of a processing and a responsiveness requirement for the host, but it's somewhere in between the two worlds, I suppose. So yeah, as I said, I can't really talk about the vendor solutions because that's completely up to them and it's something that isn't standardized. What we do have that's standardized though is what we call Vertio GPU. So this is a standard within the Oasis group who maintain Vertio. It's completely open and vendor independent. You're able to join and get involved and propose some improvements. And similarly, I'm going to be focusing on the implementations we have within Mesa and Linux, the open source implementations. There are other ones from other vendors, be they open or proprietary, but since these are the open ones, I'll use them as an example because they're the ones we can actually discuss the details of without getting into trouble. So, as I said, the concept of API virtualization is capturing these GL calls within the guest, moving them down across the virtualization barrier, and then executing them in the host as if we were just a native app running within the host. So the way you virtualize OpenGL, it's a bit of an odd one. GL implementations, thanks to its history, are a bit more complex than you might think. So to understand how we virtualize OpenGL, first we have to look at how it works and how you even implement it natively. The way GL works is it's a model where every time you need to draw something, you set up the entire state very explicitly, all of these parameters one by one. You update anything that's changed for your specific instance, and then you rinse and repeat for every draw in every frame. So all of these steps are going to happen every single frame. The entire configuration gets emitted line by line, blending, texturing, depth testing, programs to use, and then you draw. So if you have, hundreds and thousands of draw calls per frame, this turns out to be an enormous overhead. And it kind of worked well as a model when this was how GPUs worked. In the beginning, all of these calls, the calls to enable or disable blending, the calls to enable texture units, they would literally flip registers on the GPU directly. New hardware doesn't work like that at all. So it turns out that this model just doesn't match anymore, and we have to compensate for that in software. And we do this by caching. Because every time inside a GL driver, both virtualized and for hardware, every time we see a new piece of state, the driver will internally compile that to these quite large, can be tens, even hundreds of kilobytes of descriptors. We compile and store those, and we stash them away in a cache. Because this compilation process is actually quite expensive, and so is even just the resource allocation and filling the descriptors can be expensive. So all competent and performant GL drivers have this huge state cache within them, and quite complex to hide from the user that everything they're doing ends up being surprisingly expensive. And then if you're virtualizing GL, you have to unpack and you have to do the reverse on the host to execute it. So, we've compiled a way. We know state 1 has blending, has textures set up in a certain way. We've cached that away, which is nice, but then the GL API doesn't have any native notion of this. So when we go to execute it on the host, we have to kind of unpack this state back out, and we have to walk through and again, line by line, issue a function call to set every single piece of state. You can see the kind of obvious performance ceiling with this. Not only that, but again, the native driver on the host is going to be doing the same state tracking and the same state caching and similar compilation. So we're eating this overhead twice, and we're doing this tens of thousands of times per frame. And one of the other issues is that within the host, you have to take all of this complexity as part of the platform. You have to have the large and complex GL driver that's been optimized to pretend that GPUs work in a way that they don't. So there are security aspects about that as well, of how much work you do within the host. That being said, it works a lot better than you'd think. The performance ceiling, honestly, is much higher than I thought. We have this out in the world, at least tens of millions of real users, doing everything from automotive and data center type use cases, within cloud streaming, virtualized desktops, AAA games running on a whole spectrum of devices, from very, very high performance to very low cost devices. It's worked surprisingly well. But, is there something we can do that turns out to be better than this, to be more efficient, and just sort of meet in the middle? You may have guessed that the answer to this, I think at least, is yes. So, OpenGL is still in wide use, and it will never go away, but the Khronos group who produced OpenGL have now produced Vulkan. And Vulkan is designed, just as GL was originally, to be a very direct expression of how modern GPUs actually work. So the aim was to have a very, very thin driver with very predictable behavior, maximally performant, and shift some of that effort and some of that load onto the apps. It does have a couple of other principles. GL has this extremely large API in terms of surface area, very complex interactions between them, and a lot of runtime error checking. Vulkan does away with that. It has very explicitly, much more clearly than GL, enumerated valid usages that it allows you, and if you step outside those, that's on you. Your app can crash. But then the flip side to this is, because the API is so much thinner, we can do really extensive validation and checking of how we use the Vulkan API. And together with the protection and the isolation that modern hardware gives us, despite Vulkan being unsafe because it, takes these sort of guardrails away, we believe it can actually be safer than GL, just because the driver is so known and so predictable. And it's based on this, again, explicit expression of what happens. So we're doing the same thing here, where we have two different configurations of draw, but we've shifted the barrier over. So rather than placing the onus on the driver to understand which configurations are being used and to try and cache them and hide this from the app, we make it the app's problem. And the app explicitly builds and compiles these state and then just references them later on. So there's an upfront cost in doing this compilation, but when you've done that, it's very, very straight line. You request a draw, you reference the state that you built and compiled earlier, and that's it. And it's a very direct mapping to what we have with GPUs. So we have in development, similarly to Vertio GPU and VirGL, we have some extensions to that called Venus and Graphics Stream VK. These are two relatively new projects within the last couple of years, which just virtualize Vulkan and move those API concepts across the virtualization layer. So it's very, very low impedance. It's a one-to-one mapping between what you have in the guest, what you push across the virtualization layer, what comes out at the host, and ultimately the GPU hardware as well, because Vulkan better matches that model. But we still need, as I said, to support OpenGL, right? So there are a couple of projects doing this as well, which are very compatible with this model. Zinc is, again, an open project within Mesa that we started a few years ago. It's a very long-term bet on where the industry was going. Angle, which comes out of Google's Chrome and Android teams, is doing a very similar thing. Both of them implement implement OpenGL in terms of Vulkan. So the hardware vendor will provide a Vulkan driver which works for that platform, and then there's just this software translation layer on top. Normally, this is going to hurt you with performance, but if you think back to those diagrams, the way that Vulkan expresses itself to the host is very, very similar to the way that GL drivers are implemented anyway. They're very compatible concepts. And it's probably not surprising, given that Vulkan was created by all of the Khronos members who write OpenGL drivers for a living. So it's kind of just scraping out that bottom layer. And because of that, we can have a very low overhead, very performant translation. And if we use virtualized Vulkan as our platform implementation, then we can confine all of the overhead, all of the complexity and surface area of OpenGL to just living within the guest. We can make the host a smaller and more trusted surface. We can still offer that platform-independent virtualization, so your workload can be fully unaware of what it is that it's running on. You don't need to have your entire hardware-dependent stack projected right through up into every guest workload. So yeah, this is kind of an amalgamation of the two diagrams, because again, the concepts and the models are just so compatible and so similar that it's almost natural for us to take OpenGL, to reason about that within the confines of the guest, and then to push an increasingly lower level translation of what the guest workload actually wants to do down to the hardware through the Vulkan-based virtualization layer, and eventually through the Vulkan API itself to the native hardware. And we just don't have these violent impedance mismatches where we're trying to pretend that things have very different performance properties, or we compile this nice known state and we have to explode it back later on in the host to a million different calls. So yeah, in summary, graphics virtualization is here. It is a commodity thing. We're not special anymore as graphics people. It's right the way from the data center all the way down to surprisingly low-end client devices. So it's a thing we can't ignore, needs to be there, needs to be reliable, performant, and secure, exactly the same as our CPU virtualization needs to be. There are the 3 different models, and it really depends on you and your use cases and your platforms that you run on as to which is going to be best for you. The IHVs will always provide their own solutions. Lets them do SKU binning. There's licensing opportunities as well. So that's something that will always, I think, continue. But in parallel to that, these open and vendor-independent efforts are going to continue. And with some of the work we've done over the last couple to few years, we're able to now put together the pieces into something that's very low overhead, very performant, very functional, and very secure. So I hope this talk did what it said on the box. I hope it gave you an insight into how the ecosystem and how the industry works today and where it's going. If you have any more questions, I look forward to those in the session, or my email is here, so please do feel free to get in touch and we can happily discuss. Thank you.